So loud.
Morning, everyone. Welcome back. Just a couple things. So we're doing fast Fourier transform today, but I just wanted to, I had a typo in the slide from the dense matrix algorithm, so I'm going to go over it again. And we have an exam Wednesday. The same as last time, you can bring one sheet front and back with whatever you like on it. The topics are, I don't think this is in order, but like the communication primitives, sorting, dense matrix, and embeddings. So the topics that we've covered after the first exam up until now, not including FFT, and not including anything about MPI. Questions? And I put the solutions for the homework 5 online, so you can check that as well. And there are practice exams on campus also. Yes?
Oh, I'm sorry. I'm sorry. Could you repeat that again?
The whole thing?
The things that we're going to be covering.
Oh, yeah. So like everything after we did the first exam, so like communication primitives, sorting, dense matrix algorithms, and embeddings. I don't think that was in order of what we did in it, but those are the important things.
Okay, thank you.
So yeah, and not including MPI, so just the algorithms part. Questions on that? Yeah, and then and there will be, if you look at the practice exams, there's like a sheet of bounds in there about the primitives, so you don't have to write them yourself. I'll just include that same sheet. Cool. Yeah, so we're going to do a quick go back to this matrix thing, and then we're going to move on to FFT. So a couple times ago, we were talking about the summa algorithm. And if you remember, the summa algorithm is based on like these row and column broadcasts of outer product. And in the last part, so in the beginning, we just had like one element per processor because that was the easiest way to see it. But in reality, we want to do blocking. So the way that we do it, suppose we have square matrices. And remember, in the summa algorithm, the serial way to express it is for k 0 up to kn, k++ is like the most, the non-blocking way to do it. So you just do one iteration of k at a time. And the outer loop is over the inner dimension. So like the k dimension that is shared between the A and B matrices, and the inner ones are parallelized over I and j. But just for this very simple pseudocode, this is how we can write it. So remember, we're computing these like large outer product matrices that you can think of as partial sums towards the total matrix multiplication. And for blocking, in this very simple formulation, rather than going up one at a time in k, we go up b at a time in k. So that is b columns of a at a time and b rows of b at a time. And then the outer loop has fewer iterations, and the inner one, this column notation is the range. So here are columns k up to k plus b minus 1, and here rows k up to k plus b minus 1. And if you remember in summa, well, it's always in matrix multiplication, but also in summa that the inner dimension needs to line up when you do multiplication. So that is the blocking version, and same table last time. So still the block size, like if you actually think about what is happening, one block of columns in A is getting multiplied with one block of rows in B. But each one of those block rows or block columns is also is further divided into squared, or like into further subdivisions, because you have multiple processors along that row or that column. So the total size of the block row that you're doing multiplication is n over root p. That's one block row or block column, but there are root p processors in that block row or block column. So the size of the submatrix is actually n squared over p. Because it's this thing divided by the number of processors. So this thing again divided by root p is n squared over p. And the rest of it is the same. So the broadcast, the analysis goes the same way. You take the message size, which is n squared over p, and you plug it into the broadcast time. So the broadcast time is tau plus mu m times log the number of processors you have. And tau and mu are always fixed. M is the message size, so it's n squared over p. And log root p is order log p. Yes. Yep.
In the previous slide, how are you adding
don't they have different dimensions? Like if
This thing multiplied, so A has, if you think of it like MKN, the result of this matrix multiplication is a matrix of m by n, and that is what C needs to be.
so you're trying to multiply, not add it?
Yes, sorry, that should be multiplied.
Okay.
Yeah. Yes, yeah. Yes, good point. So this should be multiplied, but yeah, so it doesn't matter what the inner dimension is, it's just like the outer dimension.
No, I understand. I just saw the
Yeah.
plus. I was curious.
Thank you. Yeah, obviously. Yeah, so this part is the same. You plug in the message size, and log root p is order log p is 1/2. And the number of rounds is the same, still root p, which is the length of the processor grid. And then the total cost is number of rounds times the cost of the broadcast per round in communication. Yes, so you have n squared items, and you have p processors, and so every thing that, let's just say the processor column for a second. So every processor column in the entire column has n squared over root p items in it, and every one of the processors in that column has n squared over p elements. So just to recap, not just for Sigma, but for all these matrix algorithms, the way they work is like you have some communication pattern, you need to figure out how much stuff is getting communicated in every round, and how much stuff is getting, what is the size of the local multiplication, and that is, so those break down into communication time and computation time. And then you have a number of rounds, and you can multiply it to the total cost. Any other questions on the exact topics before we move on? So, today we're doing fast Fourier transforms. This is not an example, but we're just gonna do it. Okay, so many of you may have heard of fast Fourier transforms, even if you don't know the technical details. It's one of the most famous algorithms. There's like this column a few years ago about the most famous, the top 10 algorithms in the 20th century, and FFTs were listed on there. And they're also frequently used in scientific computing. So this is a table about problems that people are often interested in performance computing. Many of them we have done, like dense matrix algorithms, for example, and sparse matrix algorithms are what you're doing in the programming assignment. We're going to do n-body simulations next. And FFTs are one of the major ones, and these are just like the applications that they appear in. So health, image, speech, music, and browser, and red means that they appear more heavily than those. Yeah, so today we're doing FFTs. And basically the high level of how this works is you have some signal, so it's often used in like speech processing or sound processing, something like that, and you have it in an original domain, for example, a time domain. You have some sound over time, which is represented as a wave, and then you want to convert it into something in the frequency domain. And the way that happens, so this is the initial signal formulation, and through the FFT it gets decomposed into this frequency domain. And the point of the frequency domain is to try to find kind of like spikes in the frequency domain, which represent important information. And one example of it, so it's most often used in signal processing or sound processing, but it can also be used for image processing. And one way that is used in image processing is to try to do some, it's not exactly compression, is to try to find some sort of smaller representation of the image without representing all the pixels, because that may take a lot of space. And so we have an image and we want to get most of the information of the image, but we want to not use the entire space of the image because it costs something like, say you're in a browser and you don't want to communicate all the pixels over the internet to show it in the browser, you want to have some some approximation of it that gets you most of the information. So in the usual format, without any decomposition, let's say you take 25% of the pixels and you pick them arbitrarily, just the first 25%, this does not give that much information about the image. This 6.25% also, if you want to do even further reduction, gives you almost very little, almost nothing about this picture. But using the FFT, you can decompose the image into low frequency and high frequency information. And coarse information, or low frequency information, is in some sense like the most important information that captures the general idea of the data. So using the lowest frequency information, this is using 6% of it, about 6%, this is using 25%. So the point is that it can give a better picture of what the actual data is without having to just use this like arbitrary choosing, which may not give you much information. So at a high level, this is what this discrete Fourier transform is. So discrete Fourier transform is the problem, and fast Fourier transform is an algorithm to solve the problem. And this is what it breaks down to, is you have some, it's basically a matrix vector multiplication. So you have this matrix, which is n by m, so 1 to n minus 1 and minus 1, the whole thing is n by n, and you have an input, a0, a1, up to a n minus 1, and you multiply this matrix with this vector to give this p vector, represented here, which is this p of omega 0, p of omega 1, and so on, up to p of omega n minus 1. And with matrix vector multiplication, this can be solved in order n squared time. So we have done parallel algorithms for matrix vector multiplying earlier in dense linear algebra. And so we know how to do partitioning, like 1D, 2D, and so on for that. And we could, so the easiest way to do this is we could represent this function as just a matrix vector multiplying, and with a special matrix m of omega. And m of omega is given by mij is omega to the power I times j, starting from 0. So omega to 0 is just 1. And the point of the FFT is, at a very high level, is that this matrix has some special structure, which we will go into, and you can reduce this running time because of the special structure from n squared down to n log n. So to go through some notation, this mean, we're going to use this main idea of something called roots of unity, which is from, it's just from math. So roots of unity are what these omegas are. And this is just some special matrix that is going to be applied in the FFT. And a root of unity, it comes from complex numbers. So it can also be called the nth root of 1 for some given fixed value of n. And the easiest way to visualize it is through the unit circle. So we have this unit circle, and for a fixed n, there are n roots of unity along this unit circle, each represented with e to the power 2 pi k over n, where k ranges from 0 up to n minus 1, and I is root of -1. So this thing, so the angle is 2 pi over n. And you're just going around this unit circle, and k is the one that is changing, so as k ranges from 0 up to n minus 1, those are the different angles. And they can all be defined as powers of k equals 1, which is called the primitive nth root of unity. That's like k equals 1, like if you just keep raising this higher and higher powers, then you'll go around this circle. And yeah, you can say that omega is this primitive nth root of unity if omega to the n equals to 1, and omega to j is not 1 for all j between 0 and n. seen this before? Okay.
I've seen this, well, I mean, we talked about this algorithm with algo too, but also like, I'm sort of familiar with seeing this background.
Yes. Others? Any questions? Yeah, so sometimes people see this before in math, depending on the math background, but we're not going to go that much deeper than this. It's just relies on complex numbers, and all we need to do here, in a moment, I'll show some basic properties of roots of unity, and those are the things that we're going to use, but it will not be that much more complicated than this. The main thing to remember is that the easiest way that I have of remembering this is that to think of this unit circle and think of them as points on the unit circle, and depending on n, you have smaller and smaller angles on the unit circle. Oh, and the things on the unit circle are, so 1, -1, I, and -I. So the things that are opposite on the circle are negatives of each other. So 1, -1, I, -I, and here this is 8 points, so n would be equal to 8. So using the definitions that we just had of these roots of unity, we're going to show some basic properties. And the point of showing the properties is that we're going to use them later in the algorithm. So the first one is that if omega is the primitive nth root of unity, if n is greater than 0, then omega of n over 2 is -1. So this is what I was saying earlier, like on the unit circle, if you have -1, the thing that is opposite you, which is, so the thing that is at 1 is omega to the n. The thing that is at omega to the n over 2 is the thing right opposite on the unit circle, and that thing is negative to what you are. So if you are 1, then the thing opposite on the circle is -1. And we can just show that through this function. So just plug in n over 2 as the power, and this is the power for omega, so this is e to the 2 pi I over n. Omega to the n over 2, so you just plug it in, that's e to the pi I, which is -1.
Just for clarification, so like it's the primitive nth root of unity that's just like the thing raised to the 1 or 0? What makes it primitive again?
So yeah, good point. So the primitive nth root of unity is omega. So omega is the primitive nth root if omega raised to the n is 1.
Okay.
Yes, sorry. So yeah, good point. So just to recap. So so for fixed n, there are n roots of unity. The primitive one is omega, where if you raise it to the power n, then you will get 1. And all the other ones, like in between 0 up to n minus 1, are not 1. Yeah, so using that, given that omega is the primitive nth root of unity, so we know that raising omega to n will be 1. And here we use properties of complex numbers to show that if you raise that thing to n over 2, rather than raising it to n, you'll get -1. In the picture, this is omega to the 8, n is equal to 8 in this example, that is 1. And then just on the other side, omega raised to 4 is -1. And we get that just by plugging in the definitions. And the second thing is that given some even n, and if omega and v are the primitive nth root and the primitive n over 2 root, then if you raise omega to the k over 2 for some arbitrary k, you will get v raised to k. And the meaning of this is that, so you have n roots of unity, and then you can define a second unit circle with n over 2 of them. And basically, what this is saying is that the second half, will repeat the n over 2 roots of unity. So, looking at this example, so k is for 0 up to n over 2. and this is saying, so w to the k times 2 covers the second half of this space, like n over 2 up to n. And the second half of this will cover the first half of this again, because b to the k goes from b0, b1 up to bn, n over 2 minus 1. And the point, so the first thing is that if you have n roots of unity starting from the second half, they will be negated from the first half. And the second thing is that it's this recursive property that you have omega and d, which are the nth root and n over 2 root, then you will get in the second half repeating the first half. So the proof comes from here, omega to the k squared. We plug in to this equation, 2k e to the 2k times 2 pi I over n. And if you do some factoring, what this comes to is the definition of b to the k, because the definition of the roots of unity was e to the 2 pi I k over n. And so for the n over 2 roots of unity, the n over 2 needs to be the denominator. And k is still up there. The last property just uses P1 and P2. So if you have an even n, then the squares of these complex nth roots of unity are the n over 2 complex roots of unity. And then squaring those. So for P1, you have, so P1 is just saying that the second half of the unit circle is the negation of the first half of the unit circle. And for P2, we know that both of those are the n over 2 roots of unity. And so squaring those will give you the same square because like, one half is positive. The first half is positive, the second half is negative. By squaring them, both of them become positive. So this looks a bit complicated, and the high-level reasoning that we're going through this whole thing is because we're going to use these properties of the roots of unity to try to form some recursive structure in the FFT. And the high-level way this is going to work is that we have two halves, the first half and the second half, and we want to show something about how the first half and the second half are related. So going back to this is what we're going to do in the DFT. We multiply this matrix based on the powers of the roots of unity with some input vector that we got and some output vector. And we're going to get some output vector. And again, this is just regular matrix vector multiply. You could do it like that, and that would take n squared time. It wouldn't be wrong. It would just be less efficient that we can't do it. And so this famous algorithm, fast Fourier transform, originally from Cooley and Tukey, is related to polynomial evaluation. So polynomial evaluation is you have this polynomial a0 plus a1x plus a2x squared up to an minus 1 xn minus 1. And we're going to show that this is related to this matrix vector multiplication. And you can compute this with this special matrix in n log n time. And so one of the easier ways to see the FFT is through this polynomial view. So the output vector is the evaluation of this matrix vector multiplication, but you could also think of it as the evaluation of a polynomial with different powers of this omega. So if you remember this polynomial, a0, a1x up to an minus 1x, the a's are the coefficients of the polynomial, which is given by this vector. And each entry here is the multiplication of one row and this vector. And these are going to be the powers in the x, where x is set to what is in here. So this is why it's in this form p of omega to the power of something, because this is the polynomial evaluation where the x is set to what is in here. So like here, this is just omega raised to 0, so x is always 1. And that's this row multiplied by this column, just doing the dot product of C. And p of omega to the power 1 is, so the thing is in the row, 1, omega to the 1, omega to the 2, and so on, which are going to be what you get if you plug in x equals to omega in this lower thing. And so on for every row. So the powers of omega are going up just by 1 at each time here, and this is just the evaluation of what happens when you plug in omega. What you get when you plug in x equals to this thing into the row. So this is just giving you the values of x to the powers. This gives you the coefficients, and you can think of each row column row vector multiplication as the evaluation of one of these polynomials. And then there are n entries, and that's n evaluations. And so FFT algorithms are usually based on this polynomial view of matrix vector, not direct matrix vector products. But initially, this doesn't really help us without some more clever thinking, because like we can just directly evaluate these polynomials. We can plug in x, but naively, it will take us n time to evaluate one of these because there are n entries. So if we just plug in some x and do the summation, it'll cost us order n time. We have n of them to evaluate, so that will still take n squared. So initially, this doesn't help without explaining some structure of the problem. So yeah, so I was saying this FFT is based on this view of polynomial multiplication. And polynomial multiplication is giving two polynomials p and x of this form. So p of x is the same that we have been doing, and q of x is just another polynomial that has a similar form still with x, but now the coefficients are different. They're b rather than a. And if you want to compute the multiplication of these, the output degree, so if this has degree n minus 1, this is degree n minus 1, the output degree is going to be bounded above by the sum of them. So that's m plus n minus 2. And the way that you can get multiplications is you can do this the most straightforward way to do the multiplication is to do this distribution on every entry. So like the first thing would be a0 times b0, second thing would be b0 times b1x, and so on like that. And so you would get a whole bunch of terms, and some of them would share powers of x, depending on how the distribution works. And this is how you get the coefficient in C sub 1, which is the things, you can kind of think of it as like A is going up, B is going down, and those are the things that will share the same power. And so their coefficients will get added together. And the serial runtime is order m times n, because there are m terms up here, n terms up there, and you just multiply each one of them one at a time. And we have this closed form of the coefficient. So this is called the coefficient view of the polynomial, which is like the kind of one natural way that you might write it in code if you wanted to represent a polynomial is with, if you have degree n, you have a vector of length n, and each entry in the vector is one of the coefficients. We want to do better than this quadratic-ish time. And so one way that we can do better in polynomial multiplication is through what is called value-based representation. So there are two main ways that we can represent a polynomial. The first one is in what we just did, which is called coefficient representation, which is just expanding out the whole thing with a sub 0, a sub 1 up to a sub n minus 1. And then you have x squared, and so on. Another way to represent a polynomial is through points, which is what we're going to call value-based representation. So you can represent it through this kind of form. Another way to uniquely identify a polynomial is through m values. So if you have degree m, if you have m values of x evaluated at points, or sorry, if you have m values of p of x evaluated at these points, you can uniquely identify, you can come back to this polynomial by solving systems of equations. And so you can think of that as just like, you have pairs of points, like so for example, the simplest polynomial is a line where the degree is 1, and we know that any 2 points represents a line. You just draw the line for 2 points. Similarly, if you have a quadratic equation, if you have 3 points, you can uniquely identify the quadratic equation. And it turns out that you can generalize into arbitrary dimensions. And you can go back and forth between them. You can, if you have this coefficient representation, you just pick m points. You can solve the m points, and you can come to the values. And going back, you can, if you have the values, you can plug them in into systems of equations. Like you plug in p of x of I, you have m of them, and you have m equations of this form. You're trying to solve for a of 0 up to a of n minus 1, and you have x. And if you solve those, you can go back to the coefficient form. So anyway, the point of this is that the second way to represent this polynomial is if you have degree m, you can uniquely represent it with n points. And at first this seems like a less natural way to represent the polynomial. Like we're used to representing it in the coefficient form, and that is easy to represent in code as well through this array that I was talking about. And the reason that we're interested in this is because it turns out that you can multiply faster in value form. You can multiply the points directly. So in value representation, again, we're coming back to this problem of multiplying two polynomials, p and q, and we want r. And suppose that we know p and q at m plus n over minus 1 distinct values, which is, so remember that you need, if you have degree m minus 1, you need one more point than that. And the reason, the earlier thing was the output degree of p and q is m plus n minus 2. So you need one more point than that to identify r. So suppose that we have p and q at m plus n minus 1 distinct values, which is how many points we need to uniquely identify r. And then we can compute r at m plus n minus 1 distinct values just through multiplying the values of p and q that we have evaluated. So we have p of x of 1 and q of x of 1, or sorry, x of I at this many values. So we have this many x of I, we have this many x of I, and we have this many p of x of I and q of x of I. And we can get this many r of x of I by just multiplying the two outputs together. Yeah, because like when you multiply the polynomials, every point is just the multiplication of the two input points. And using this, we can multiply them in m plus n time, rather than previously it was m times n time in coefficient representation. But in value representation, it becomes additive rather than multiplicative. So this seems good. It seems like we're going in some direction, which is that we have reduced the time of the multiplication. But we've made other things more complicated, which is, first, value-based representation is not, you need the coefficient representation in some sense to get to this value-based representation, because if you just have, like if you have m points, you cannot easily get another point unless you go back to the coefficient representation plug in another x and do the evaluation. So that's one issue. Another issue is that it's easy in the code to represent polynomials in this coefficient representation. Just put the coefficients in an array. And finally, to specify, if we started with value representation for each one, p has degree m minus 1, so we would have m points to fully specify it. Q has degree n minus 1, so we would have n points to specify it. But we assumed that we had n plus n points, because we wanted to specify the multiplication of them. So if the issue clear, like if you have only value representation for p and q, it's not immediate how to get the full number of points that you need to get r. So you have fewer points. And so, yeah, how can you get the value of this many distinct values? How can you get the values at this many distinct points without the coefficient representation? So, with these issues, we cannot immediately start just with the value representation, because one issue is that you can't do the evaluation. Another, related to the first issue, is that you can't get more points without being able to do evaluation. So, due to these issues, we're going to use two of them. We're going to use both the coefficient and the value representation. And it's natural to start in the coefficient representation, because that's like normally what you would get a polynomial in when you write it in the code as your input. And so we will start with the coefficient representation. So it's natural to start in the coefficient representation, and another good thing about it is that we want to do this evaluation at all the points, and you can do that with the coefficient representation. So the high-level algorithm is that given p and q in coefficient representation, we're going to evaluate it at m plus n minus 1 distinct axes. And so we're going to convert. So basically what this is we're converting p and q into value representation by evaluating it at m plus n points. And so, naively, this is going to take n plus n squared time, n plus n quantity squared time. And step 2, once we have done this, is that we do the multiplication now that we have these evaluated points. And that takes linear and additive time, so that's good. It's n plus n. And finally, we convert r of x back into the coefficient representation. And we can do this through systems of equations. It's not ideal. Naively, it would take cubic time in n plus n. So we want to reduce these times. At first, it seems like we didn't improve anything. Actually, it seems like we did worse, because if we just did the regular distributed way, it would take this n plus n squared time to do the multiplication. So yeah, we reduced this down to linear, but this cost multiplication time, and this costs more than that. So initially this seems like not a great way to go, but maybe this is why this is one of the most famous algorithms, because with some observation you can get these times down significantly. And the key idea behind the FFT is that you have a choice in the values of x that go into the evaluation or the matrix vector multiplication in the initial formulation. And we're going to choose the values of x such that you can save work in the evaluation. So this is how it's going to go. Assuming that we have a power of 2 number of coefficients that we need to evaluate this polynomial. And can represent it in the coefficient form of just sum up I equals 0 up to n minus 1 of a sub I of x raised to the power I. So this is just the summation form of that expanded out coefficient from earlier. And the high level idea is that we are going to want to choose negative opposite pairs of each other. So let's just consider 2 points for now. X equals to alpha and x equals to negative alpha, where alpha is just any number. And if we plug it into this form, we can split this thing into even and odd parts. So this first part is the even part, and we're trying to evaluate this polynomial at many points. And the high level idea is that we want to overlap the work in doing this evaluation. And so one way we can do it is to choose, if you choose alpha and negative alpha, like these corresponding pairs of negative points, you can split this up. So the first one is all the terms with even powers. So this is going I up to n over 2 minus 1, and this is a to the 2i raised to a to the 2i times alpha raised to 2i. So that is all the even terms in this thing, plugging in alpha. And the odd terms are similar, except you can pull out an alpha. So this a to the power 2i is the same, because multiplying this would just get you alpha to the 2i plus 1. And if you look at the negative case, with negative alpha, the first half of all the even terms is the same, because the powers are all even. So if you raise anything to an even power, you would get something positive. So these are all positive. And this thing is just the thing flipped. So this is all alpha raised to some odd power, 1, 3, and so on. And that would give you negative alpha times the immediate even power right before that. And if you notice, these two, minus the plus and minus part, are the same. And these first halves are actually exactly the same, with no change in the sign. So these are two overlapping terms. And if you computed this half and this half for p of alpha, you would need to do no more work to compute p of negative alpha, because you have this whole thing, you have this whole thing, and you just subtract this rather than add it in. And you can do that for all the points. So here we just did it for 2, but we actually need to do it for like n points. So you do like, you choose n over 2 distinct alphas, and then they would all correspond to n over 2 distinct negative alphas. And to evaluate n points, you would actually need to do the work of n over 2 points. Questions on this part? So this is the first step towards the FFT, because it's based on these positive and negative pairs. And this is the first level, it's sometimes the first level of the recursion, because we kind of chose like half of the points to have negative pairs in the other half. But that only cut down the work by half, and I promised that we would cut it down to n log n, so you need to further do the recursion. And the way that the further recursion is going to work is that actually these are also polynomials. And so now these are each polynomials of size n over 2. We started with a polynomial of size n, and you can think of these as two subproblems of size n over 2. And so we want to try to apply the same trick into each of these halves. Okay, so this is just explaining a little bit what I was saying earlier. So you have this even half and this odd half based on the powers, and they are both overlapping with each other if you evaluate alpha and negative alpha. Plugging this in, p of alpha is the even polynomial with alpha squared in it, plus alpha times the odd polynomial with alpha squared in it. And if you evaluate it at negative alpha, it's basically the same, but with minus instead of plus between them. And so if you had this and that, then you can avoid any recomputation for this part. So the high-level strategy is we need to evaluate p at endpoints. You choose the first half as distinct points, and the second half as the negative of that. And so evaluating the n coefficient polynomial at n values becomes evaluating two n over 2 coefficient polynomials at n over 2 distinct values. So we cut down the work in half at the first recursive step. And this runtime is given by 2 Tn over 2 plus order n. And this is the same recurrence as for example, like merge sort or quicksort in expectation. In merge sort, this order n is given by the merge step. In quicksort, this is the partition step. But we know that those are n log n, and so we hope that the whole runtime of this thing will also become n log n. Okay. Yeah. And so we want to apply this strategy recursively. We are going to, in this next recursive step, we are trying to evaluate two n over 2 coefficient polynomials at n over 2 points. And the points that we evaluate these two at also need to have the same property where the first half and the second half are positive and negative pairs. So we would ideally like this property that we choose these x points, x to the I. So for x of I, this is correspondent in the second half at the first step of the recursion is negative x of I. And in the second half of the recursion, now x squared, this is the corresponding value in the second half of the second step of the recursion. So now we are focusing on the case of the first n over 2 points. And we're trying to make the first n over 4 and the second n over 4 positive and negative pairs. And the issue is that if you look at what happened here, this became alpha squared in the next step because these were even and these were odd, and the even ones are like 0, 2, 4, and so on. So we want this property all the way down as well, when you cut it into 4, that the first n over 8 are the inverses, are the negatives of the second n over 8 when raised to the power 4. This is not possible, of course, for real numbers. Any real number squared is also a positive number. And that's why in the very beginning, we had this detour into complex numbers. Because you can choose complex numbers that have this property, but there's no real number that has this property. Yeah, and all the way down, up to the general form is for some power 2 to the k. And so to choose these points, the idea is to choose these complex numbers, and it turns out that the roots of unity also have this property that we showed in the beginning. So you can think of this as cutting, so like the first level of the recursion is the n roots of unity. Now the second half, you have the n over 2 roots of unity, n over 4, and so on, all the way down. And we were also showing that when you raise the power, you come back around, like you repeat the things in the unit circle. So that's why we showed that, because we're raising these powers squared and 4 and so on. So this part is a bit hard to get, I think. At least I had trouble when I was first getting it. And the high-level intuition is that you want these positive and negative pairs, and it it works to just choose real numbers for the first level of the recursion, but it needs to work for every level of the recursion. When you get new subproblems of n over 2, each of those halves need to also have positive and negative pairs. And also the issue is that you cannot choose the x points as you go down the recursion differently. Like the points need to be fixed up front. The points that you're evaluating the polynomial at, they can't change when you evaluate the subpolynomials, because that would just become new points. So the points all need to be fixed up front, and they need to have this property. And this is just showing, kind of similar to what we were showing earlier, that if you choose x of I is omega to the I, where omega is the nth root, then this is the second half, and raising it to the power 2 cubed so the sum part is I to the n over 2 to the k, the top part is raising it to the power 2k plus 1, so this is what you're getting at the kth level of the recursion. That it will come out to negative of x of I raised to 2k plus raised to the 2k minus 1. So this is saying that the second half is the negation of the first half, and then vice versa. And this proof is just an extended version of what we had earlier. And so the first level of the recursion was evaluating this n coefficient polynomial at n values. The subproblems are evaluating two n over 2 coefficient polynomials at n over 2 values, and you cut it down at every level of the recursion. So every subpolynomial also has this property like the even and the odd are overlapped, and so you only need to evaluate one of them to get the second one for free. And that's where this recurrence comes in, and the whole thing is n log n. So yeah, so there's two main tricks in this. One is to convert between the coefficient and the value. So basically, the high-level flow is like you start with the coefficient representation, you go to the value representation using this algorithm, you multiply using the value representation, and then you come back to the coefficient. So like, it's kind of like a U shape. Start with the coefficient, you go into the value form because it's faster to multiply, then you go back to the coefficient form. And the way to efficiently convert between coefficient and value form is through choosing the points correctly. So this is just an example. Let's say we have p of x, and we have 8 degree 8. So this is a0, a1, x, up to a7, x to the 7. And we represent it as this polynomial, 0 through 7. And the even part is just the even terms. So a0 plus a2x, a4x, a6x. P odd, a1, a3, a5, a7. And you can represent, using this, if P is represented with all the terms in it, 0 up to 7, you can say this is P sub 0 and P sub 1, 0 for even and 1 for odd. So P sub 0 is 0, 2, 4, 6, and P sub 1 is 1, 3, 5, 7. And then similarly, if you cut down one more level of the recursion, P00 is 0 and 4, because these are the even terms when you go one level down. P01, the odd terms in this one are 2 and 6. And then similarly for this. So you can kind of see how the recursion is going in that it sort of follows this tree-like pattern where every, like, when you make the polynomials, you can append additional bit string based on, in some sense, which direction you went based on choosing the even or the odd. Yes.
And I'm guessing it's the reason why you make this parallel is because it has to fall after two concurrent occasions. Or was like the first level, right?
Yes, exactly. Yes, good point, and we will go there in a moment. So the way that we're going to make this parallel is that it does exactly follow the hypercube, and yeah, and so you kind of get the hypercube from this tree-like decomposition. Other question on screen? So this is just breaking it all the way down. At the top, we started omega 0 up to omega 7 with p 0 up to 7. The two halves here. Sometimes if you go left, then it becomes left is even, right is odd in this picture. And so the first level, this is the even polynomial, this is the odd polynomial, and both of them take in these terms omega to the 0, omega squared, 4, 6. So at each level of the recursion, sometimes the input becomes x squared because I'm not going to go all the way back, but when we decomposed it into the even and the odd, the summation was over n, the summation was over n over 2, and then the powers increase. And if you further go down, this is the even and the odd part of the even polynomial in the first level of the recursion. So the even parts are every other one, starting from 0, so 0 and 4 here. The odd ones are every other one, starting from 2, so 2 and 6 there. And then similarly, this also breaks down into two subproblems, P10 and P11. So we're just appending the bit string to the end of which one. So like, this gets appended 1, this got appended 0, this got appended 1, depending on if you're going even or odd, the level of recursion, and so on. And you can see that these are they're not exactly the bit representations. So like, it does work for 0, 0, 0, and 1, 1, 1. So this is 0, this is 7, but 4 is not 0, 0, 1. But it actually works out that if you flip them, you get the number. So 0, 0, 1, you flip it, it becomes 1, 0, 0, which is 4. And 1, if you flip 1, 0, 0, you got 0, 0, 1, and that is 1. So if you make this bit string representing which direction even or odd you went, it becomes the reverse of the bit string in the number. And that is how we're going to find the pairs in hypercube. So, just to recap a little bit, we have this matrix vector product in the beginning, and it turns out that if you specify your matrix in a special way, that you can cut down the cost of the matrix vector product from n squared to n log n. And just to be clear, it doesn't work for any choice of x. It only works for this very specific choice of x, that you can overlap the terms with this positive and negative pairs. You cannot do arbitrary matrix vector product in n log n time. So discrete Fourier transform is this problem of multiplying this n by 1 vector with the special matrix based on omega, and FFT is this polynomial-based representation to compute this specific matrix vector product in n log n time. And yeah, this is how the hypercube looks. So normally time goes from left to right, but here it's a bit easier to illustrate it going right to left. And so here at this level 0, we have t of omega 1, t of omega 0, t of omega 1 up to t of omega 7. And we're basically trying to follow that tree that we were looking at earlier. And the first step is that the even and the odd. So in every step you decompose the thing into two subproblems, like the left and the right half. And basically what's happening is that the rank I is computing the evaluation at some omega of raised to the power I. So at the end, if you have n ranks, we're trying to compute the evaluation at omega 0, 1 up to omega n. And minus 1. And so in the first step, the partner is as far away in the hypercube as you can go, which is like the top bit is set, or unset. And in the second level, the subproblems become the two halves. So then your partner is whoever is as far away in this subhypercube, and then so on until there. You also have these horizontal connections, which are coming from left shifting. So the partners in the hypercube are just based on the hypercube itself, but there are also additional horizontal connections to do the combination of the polynomials. And that comes from left shifting the rank index. And after all of this, there's just this really tiny bit of code. For every rank, so everybody has some rank, let's assume we have n ranks in the beginning, and we just reverse the bit string. So the reason that we're reversing the bit string is, if you remember in the tree picture, the leaf order in the tree is the reverse of which power of omega we're computing. So we reverse the bit string, and for I up to t minus 1, which is the number of bits in the string, the partner is rank to the I, or rank XOR to the I, so that's the partner in that round, and we are sending and receiving some stuff. And what we are sending and receiving is U and V, but the computation that is happening, if we look at this, is U plus MV, or V plus MU, where M is some power of omega, and this flipping of U and V is just depending on who is the left and who is the right child. So in terms of this is like the even part, and this is the odd part. And where the even part or where the odd part comes from depends on if you're the left or the right in this tree. And the way that you determine that is based on the bit representation. This is pretty much the end, but the last step is, oh no, there's a couple more after this. So one more step in the FFT is that if you have more data than processors, which is the common case, and so you want to solve this problem of size n on p processors. And the way that we do that is basically to cut you still try to map this processor tree or you're trying to cut the recursion tree onto the processors, but just don't recurse all the way down to problems of size 1 to solve subproblems on the local processor once you get it small enough. So the p sub trees at this level log p. So once you get to level log p in the tree, there are p nodes, and there are p more subtree. Like each one of those has a subtree after that, but now each of those represents one subproblem that can be solved on the processor. Yeah. And then the log p levels, the higher ones are computed in parallel.
When we get to the leaves of the tree, we have since we have this like in value form, we can do that multiplication locally fast. Is that right?
Mm-hmm. Yes,
Okay.
exactly. Yeah. Good point. Yes. Yeah. Basically, yeah, we're trying to. Well, this is just the part that does the evaluation.
Oh.
Yeah. Sorry. So this entire thing is that we're in coefficient form and we want to go to value form efficiently. And then the step after that is doing the multiplication in value form, but you can do that in linear time. No, just if you, that part is really easy because if you have like endpoints of p and endpoints of q, then you just split them up in parallel on the processors and then multiply them one by one like that.
Okay.
Yeah, good point. So this entire thing, this complication is just to convert, is to do the evaluation, to convert from the coefficient into the value form. So that was step 1 in this 3-step process. Yeah. And then the time becomes n log n over p. The computation time becomes n log n over p because the subproblems can now be solved on the processors. The communication time is tau log p plus mu n over p log p, because there are p levels, or sorry, there are log p levels of this recursion that need to get communicated between the processors. Each of them needs to communicate a problem of size n over p. So the entire problem was size n, and you just cut it up onto p processors. So that's why the problem is size n over p on each processor. That's where that message size comes from. So that whole thing was step 1. Then the second step is now easy. You have n points of p, n points of q, and you multiply them to get n points of r. Now we want to convert r back into coefficient form. And originally we said that we can do that through matrix conversion, but it's going to take n cubed time if we want to do it that way. You could try to pre-compute these inverses, but it depends on n. Like you would need to make a different one for every n, which is probably unrealistic. And so this part is called like, sometimes if you look at it online, it's called like inverse FFT, which is just the last step of converting the value representation back into coefficient representation after doing multiplication. And it turns out that this inverse matrix has a very simple structure similar to the original one. So if you remember, originally we were trying to multiply this special matrix m omega with this vector a to evaluate the polynomial. To get a back, you can multiply this inverse of m omega with this p. And turns out that this inverse it's basically the same as m. There's this normalization factor of 1 over n, and then instead of m of omega, it's m of 1 over omega. But that still has the property of the roots of unity. So the important part is that this m of 1 over omega still has the properties of the roots of unity that we were talking about earlier, because 1 over omega is just omega to the negative power. And so it's like you just go backwards in the unit circle. I want to skip this proof. You don't need it, but the high level idea is that the inverse, you don't actually have to evaluate, or you don't actually have to compute the inverse. The inverse has this really nice structure that not only, so it has the same property as the original omega, but just go backwards with this tiny normalization factor. So in some sense, it's free to get this inverse, and you can apply the same strategy again. So the last step, step 3, which is you have your points in value form. You want to convert them back into coefficient form. You just use the same idea of the FFT, but in reverse. On this now, rather than m of omega, it becomes m of 1 over omega. And then you can get that time also down to n log n. And so the entire polynomial multiplication becomes n log n rather than n squared or even n cubed if you had to actually compute the inverse. Questions? And I added this, I'll put all the slides online, but this video is pretty helpful also for additional